Okay, good morning. So what I thought I would do this morning is walk you through this Excel spreadsheet for the worksheet that I gave in class. I wanted you to see me do this in Excel so that you would understand how to do the test for independence where there's more than one column. So I showed you in the PowerPoint, remember that we had a slide that showed more than one column and more than one row. So in this case, calculating the expected values is going to be a little bit different than how we had been doing it. Because before, like even on the front side, we only just had soap operas, right? And we had 300 students, and we divided equally what we would have expected to see versus what we actually saw. We could look for differences that way. So, because we were told what to expect. We were told that 25, 30, 25, 20% of the students, respectively, were watching these shows. So the next semester, we were basing our question of whether viewing habits have changed on what we saw the semester before. So you had to calculate the percentage to get the actual number. That's done. Here on the test for independence, it's a little more complicated, and it's more difficult to keep straight. So if you're, I think I'm sharing this slide. I mean, this Excel spreadsheet. I'm thinking it's doing it. I told it to share it. Let's see. Make sure, share. Okay. Should be able to see it. I don't know if it's happening or not. All right. So the first thing that we have, you'll see on the spreadsheet, what I did was I drew out the table that's on this piece of paper. So you'll see male and female, and then I've color-coded the differences so that you can see what's going on. Oops, that didn't work like it was supposed to. Let me go back and change that real quick, because those are supposed to be red. Thought I had this all fixed before I started, sorry. Okay, so as you can see, under each attribute, whether it's appearance, performance, or price, you'll see the observed frequencies, which match up with what you see in your table on your piece of paper. So there's the 100, 80, 50, 170, 35, 65, under each column respectively. Okay, so the question is, how do you get the expected value for each of these attributes for males and females? Well, remember what I told you about marginal distributions. So the first thing you have to do is calculate the row totals, right, for male and female, and that you can see for males it's 185, and for females it's 315. So clearly females were oversampled, if you will, in this. The total for the sample is 500 people. And then under appearance, for both male and female, 180 people preferred appearance when purchasing a car, 220 people preferred performance when purchasing a car, and 100 people preferred price when purchasing a car. So how do we get those expected values? Well, if you look, so let's take the first box, which is the males under appearance. After you've calculated the marginal distributions for the rows and the columns, you'll see in the formula bar up here, what you're doing is you're taking the row margin times the column margin, right? And then you're dividing it again by the row, by the total, right? So 500. This figure is the result of taking this, the 180, which is the column margin, times The row margin, so we're only looking at males, so we're going to take that 185, we're going to multiply the 185 by the 180, and then we're going to divide it by the total population for the sample, 500. And what we wind up with is 66.6. So we would have expected 66.6 males to say appearance was the factor that drove their purchase. Now, you could, watch this. Let me get back up here. You drag that formula down and see what happens. You get that error. So double click on the formula. All you have to do is move the boxes up. Sometimes that's easier. Make sure that the boxes that are supposed to be in the formula, which here again, you're looking at row margin and column margin, and the total sample size, which is 500, is there in that cell. And you do the same thing again. Here we're expecting 220 and 185 for males, 220, 315 for women. So you're going to multiply the margins and divide by the total. Here we would have expected 81.4 men to prefer performance and 138.6 women to prefer performance. Instead, we saw 50 and 170 respectively. You do the same thing on the price. So that's what those represent, are the how I calculated those expected frequencies. That's that first table. So from there, once we have the frequencies observed and the frequencies we expect, we can then go through our chi-square formula. Again, it's a little more complicated because you're not dealing with just one row. So I took you through each step for each cell. So the first set of boxes in cells A through D, A9, A10, through D9 through D10, you'll see what is that first part of the chi-square formula, which is frequency observed minus frequency expected, right? So you have simply to point at the boxes. Here you have frequency expected, right? 66.6 minus 100. And when you hit enter, it gives you negative 33.4. And you do the same thing. Right? So now we've got that frequency expected minus frequency observed part of the formula. And then the next step is the frequency observed minus frequency. I keep saying it backwards. Sorry. Frequency expected minus frequency observed in parentheses squared. So now we've got to square these values in cells B9, C9, D9, and B through D10, right? We're going to square those values, and that's what's happening in cells B13 and 14, C13 and 14, D13 and 14, okay? The next thing in our formula, okay, so we've done the difference between observed and expected. We've squared it. The next thing that we have to do is divide it by expected. So this is the third set of boxes for each characteristic, again. So if you look at B17, you'll see I've taken the squared value of the difference and I've divided it by the frequency that I expected to see for each of those attributes for each sex. All right, the very last thing that the chi-square formula tells us to do is to sum up all of those values. So here at 45.99, which is that combo box of B and C, 20 and 21, you'll see the summation formula in the function bar. Sum the values in those last 6 boxes, and what you get is the 45.99. That's the calculated value of chi-square. So we have one more thing to do before we can go to the table. We have to calculate our degrees of freedom. Now, when we have a single column, you know that it's really simple. It's just whatever the number of variables are in the column minus 1, because you just need that one space to move around. Here we have 2 rows and 3 columns. So you're going to need space in the rows, and you're going to need space in the columns. So how do you figure out how many degrees of freedom you need? Well, it's pretty simple. You take your rows, it's R for row minus 1, and you multiply that times the number of columns minus 1 that you have. So it's R minus 1 times C minus 1. And in this case, we have 2 rows, so 2 minus 1 gives you 1. And we have 3 columns, so it's 3 minus 1 gives you 2. 1 times 2 is 2. So you have 2 degrees of freedom. Now you can go to your chi-square table, which I don't have one right here, but you'll have one today after class. So you go to your chi-square table and you locate 2 degrees of freedom and you move across, and you know we're testing at 0.05 alpha. I didn't say that, but we are. So we move across the table to 0.05 alpha, and at that juncture, you find that 0.05 alpha at 2 degrees of freedom is 5.991. So that's your critical value. That's the stop sign. Well, now you have something to compare your calculated value to. Now, if our hypothesis says there is a difference between the characteristics that influence women's choice in cars versus men's choice in cars, we can test that. If our chi-square value was less than 5.991, we would have to accept the null, right? That any differences that we see are attributable to error. Instead, what we see is 45.99 as our calculated value. That's like 9 times larger than the critical value, right? Because that's what the table told us. This is what we should expect to see if the null is true. We have a much larger calculated chi-square value. So we get to say in our decision rule, you know, the decision rule is chi-square equals 5.991 at 2 degrees of freedom, 0.05 alpha, right? This result is significant at the 0.05 level. If you go to the chi-square table, let me see if I've got one up right now. Well, I'm guessing here, but I would suspect that the 0.01 level, you're probably going to see a figure somewhere around 3 times that value. So 14, 15 would be the critical value of chi-square. Let me look real quick. Chi-square table. Let's see how right I am. All right, I'm going to move the camera as soon as the table comes up so you can see it. Come on. Go, little gerbils. My computer's going to lock up. Too many windows open, boys and girls. Well, I'm not going to waste any more time with that, but oh, here we go. So let me move the camera for you. I don't know if you're seeing this because let me see what you're seeing. Well, where's my thing? Okay, so here's the 2 degrees of freedom, and we slide all the way across to 0.01. Oh, so it doesn't even go to 0.001. This table doesn't. But look, can you see it? Here it goes. It's really bright. This camera is not showing it. So let me back it up a little bit. Okay, so at 0.05, excuse me, at 0.01, which is 99%, 0.01, the critical value of chi-square is 9.21. So, okay, so it's probably closer to, at 0.001, which I don't know if there's a table, if I can find a table that'll go that high without like really digging this morning, but just know that what you have here are significant results at the 0.05 level. So you can say yes, you can definitively say there is a statistically significant difference between men and women with respect to attributes that influence their car buying purchases. See how easy that is? Okay, I hope this thing showed up. What I'm going to do is put this little worksheet inside the, I guess I could put it in announcements, and that's where this video will be too. All right, see you guys in class. Meeting controls.